Assalamualaikum warahmatullahi wabarakatuh. In this meeting in airport design class, we will talk and discuss about the effect of aircraft performance on runway length. In the last meeting, we discussed about the factors that affect the runway. There are environmental effects and aircraft performance characteristics. We already talked about the environmental effects, so today we will discuss about the aircraft performance and the runway length. First, we should have to know about the characteristics of the aircraft performance. So after that, we can decide the length of the runway. So I have a video that may help you to understand about the aircraft characteristics. One of the important characteristics is critical speed of the aircraft when it takes off. So you can look at the video.
Basic runway length is determined by airplane performance, and to calculate it, we need to analyze the critical moments in an aeroplane's takeoff sequence. A plane hits 6 critical speeds during takeoff. The first is the stall speed. This is the minimum speed at which a plane will remain airborne. This is not used as the takeoff speed, as any decrease in speed due to fluctuations in wind or orientation of the plane will cause the plane to fall. The next critical speed is the minimum control speed. This applies to multi-engined aircraft only. If a multi-engined aircraft loses an engine, the uneven thrust between the wings will cause the plane to turn. This is called yaw in aviation. To counteract this, the rudder will be deflected to provide the opposite yawing moment. The rudder needs air passing over it to work, and thus the minimum control velocity is the velocity at which the rudder can provide enough of a yawing moment to keep the plane straight in the event of an engine failure. The next speed a pilot needs to worry about is V1. V1 is a line in the sand for pilots making decisions whether to abort a takeoff. If something happens before V1, like an engine failure, the pilot must abort the takeoff. If it happens above V1, they must continue with the takeoff, as it would be unsafe to stop. This is the most important speed for runway designers. At this speed, the plane will need enough distance on the runway to safely bring the plane to a stop, which is exactly the same as the distance needed to reach V1. The resulting total runway length is thus called the balanced field length. Back to that in a moment. The fourth critical speed is VR, or the rotation speed. This is the point the plane can begin to lift its nose and begin its ascent. The next speed, which results in some of the coolest testing videos, is the minimum unstick speed. This is the speed the plane can take off at its maximum pitch, which is actually the point where the tail skid hits the ground. This is a video of a test pilot testing that speed. Since this would be incredibly uncomfortable, the actual takeoff speed is at least 10% higher than the minimum unstick speed. At this point, no part of the plane is touching the ground and it is officially airborne. It must then accelerate to its climb speed, V2, which it must achieve with a minimum clearance of 10 meters from any obstacle. With all this in mind, we can begin designing our runway length.
In the video, we have no 7 critical speed of the aircraft, but we will talk more about 4 critical speed that may have the most relationship to design the runway length. So this is the 4 critical speed of the aircraft. The first is the decision speed, or we can call it as V1, and the second is the rotation speed, or VR. The third is the lift off speed, or VLOF, and the initial climb out speed, or V2. So let's talk about the decision speed first. So the decision speed, or V1, is the speed at which engine failure is assumed to occur, and it's referred as critical engine failure. So if the engine failure occurs before the decision speed is reach, so the pilot should cancel the takeoff. So if we have an aircraft here, and when it reach the V1 and the failure occurs before the V1 is reached, so the pilot should cancel the takeoff and it's going to the stopway. And if the failure occurs after decision speed is reached, so after the decision speed or V1 is reached, so the pilot should continue the takeoff. Like if in failure occurs after the V1 is reached, so the pilot should continue the takeoff, because if the pilot decided to cancel the takeoff when the decision speed is reached, it may more dangerous for the aircraft and the passengers. So the pilot should continue the takeoff, and maybe after that they decided to return to base to landing. So that's the decision speed in this plot. And then the rotation speed, or the VR. The VR is the speed at which pilot initiates rotation of the aircraft. So the rotation of the aircraft is to cause a raising of the nose gear. So in the VR, the aircraft is start to raise the nose gear. And the third is the lift off speed, or fill off, is the speed at which the aircraft first becomes airborne. So this is the fill off. The fill off is when the aircraft becomes airborne, or there's no gear, or there's no part of the aircraft that touch the ground here. And the last is the initial climb out speed, or V2, is the minimum speed at which the pilot is allowed to climb after attaining a height of 35 feet above the takeoff surface, or this is the 35 feet above the surface. So the speed of the V2 is may higher or almost equal to the decision speed. This is the decision speed, so the V2 is maybe higher than V1 or almost equal than V1. So this is the 4 critical speed of the aircraft. For information, the speed is determined by the aircraft manufacturer, so it will be given. So before we discuss more about the runway length, let's recalling the definition that we already learned before, because we will talk about this when we want to design the runway. As for takeoff run, takeoff distance, accelerate stop distance, and landing distance, we already learned about this, but maybe in a different name, like TORA, TODA, ASDA, and LDA. Actually, it's quite same, but in this definition, we define this as more basic. It based on the aircraft performance, so it will defined at the detail one, a more detailed one. So let's talk about the takeoff run. So takeoff run is the distance for the acceleration of the aircraft from the brake release to the aircraft lift. So this is from the brake release to the aircraft lift plus the safety factor. And for takeoff distance is the distance to accelerate the aircraft from brake release until the plane is lifted and then starts to climb of the height of 35 feet plus the safety factor. And for accelerate stop distance is the distance for the acceleration of the aircraft from brake release to V1 and the deceleration to stop plus the safety factor. And the landing distance is the distance from the threshold for the aircraft to complete the approach touchdown and deceleration until it stops plus the safety factor. So the takeoff run is from the brake release to the aircraft lift. The takeoff distance is from the brake release until the plane is lifted and start to climb at the height of 35 feet. And the accelerate stop distance is from brake release to V1, and if there is an engine failure before reach the V1 and the deceleration to stop, and the landing distance is for aircraft to complete the approach, touchdown, and deceleration until it stops. And the last two definition is we already know. The first is clearway. So the clearway is a certain area at the end of the takeoff runway, and the stopway is a certain rectangular area at ground level. It should have to be at ground level and located at the end of the takeoff runway. And the stopway is prepared as a stop for the aircraft when the takeoff is cancelled. So this is the definition that we should have to remember again, because we will use this in next discussion to determine the length of the runway. Now let's talk about the effect of aircraft performance on runway length. So this is based on Federal Aviation Regulation or FAR. FAR are mandates for controlling all aspects of aviation in the United States. So it's based on the US, and the regulations are established and enforced by the FAA, or we call it with Federal Aviation Administration in US, because in the world of aviation, FAA and ICAO are the most common regulation to follow for aircraft regulation. So this is the FAA one, and these regulations is related to turbine aircraft. So this is for turbine aircraft. Consider three general cases for safety operation. These cases will affect the length of the runway. So the first is normal takeoff cases. Normal takeoff cases where all engines are available and sufficient runway is required to accommodate variations in lift-off techniques and distinctive performance characteristics of this aircraft. So this is when the aircraft is take off in a normal way. And the second is the engine failure cases, so where sufficient runway is required to allow aircraft to continue the takeoff despite the loss of power or else brake to stop. So this is when the aircraft has engine failure. And the last is landing cases where sufficient runway is required to allow for normal variation in landing technique, overshoots, poor approach, or else. So this is the three general cases that may happen in the turbine aircraft. So this is for turbine aircraft. So how about the piston aircraft? So as for piston, the case like the above criteria, this criteria, but the first criteria or the normal takeoff cases is not used. Why? Because in the piston aircraft, engine failure occurs commonly than the turbine aircraft. So for piston aircraft, they just have two cases. The first is engine failure cases, and the second is the landing cases. So the turbine aircraft is actually more dangerous than or have more risk than the turbine aircraft. And then after we know the three cases, the runway length is the longest runway needed between three criteria. So from these cases we will know the length required, and from these cases we also know the length required for the runway, and also from the landing cases we will know the length of the runway that we need. And the runway length is the longest runway that from here, and it will become the ARFL or the basic length, although ARFL is given by aircraft manufacturer. We should have to know how decided the ARFL. First of all, let's talk about the normal takeoff cases. So the normal takeoff cases is the runway length requires for a normal takeoff with all engines fully operating. So in normal takeoff cases, we have lift-off distance from here to here, and we also have the distance to 35 feet. This is the distance when the aircraft reach 35 feet from the ground. Next, so this is the vertical alignment. So this is the runway, and this is the lift-off distance, or we will call it with LOD. And then there is here is 115% multiplied by LOD is here, and then we have the TOR, but the TOR, how we calculate it with these equations. So the TOR is TOD1 mean CL1 maximum. Then we have the distance when the aircraft in 35 feet from the ground. This is the D35 one, and the takeoff distance is 115% multiplied by D35 one, and this is the clearway. So this is the equation to calculate the TOD, TOR, and the CL1 maximum. For information, not all of this distance has to be of a full strength pavement. So that must be full strength of pavement is just from here to here, or the takeoff run, as the clearway is not have to be a full strength pavement. So a clearway is defined as a rectangular area beyond the runway not less than 500 feet wide and not longer than 1000 feet in length, centrally located about the extent center line of the runway and under the control of the airport authorities. So this is the clearway. The second cases is the engine failure cases. So the engine failure cases described as the case where one engine fails at critical point during an aircraft takeoff roll and the pilot makes an immediate judgmental decision whether or not to continue with a takeoff or perform an emergency stop. So if there's an engine failure below the V1, so the pilot should have to make a cancel the pilot should have to cancel the takeoff. So the aircraft is going to a stopway, and if the engine failure above the V1, so the pilot should have to continue the takeoff here. So the engine failure cases should have to accommodate both of the decision of the pilot, both when the pilot decided to continue the takeoff or the pilot decided to stop the takeoff. And the stopway at least as wide as the runway, so the width of the stopway at least as wide as the runway, and must support airplane without damage in aborted takeoff. And the clearway minimum 500 feet wide, so this is the clearway, no higher than the end of runway, clear of fixed obstacle. So this should have to fix from any obstacles and under the airport control. Then this is the vertical alignment. This is the runway, and we have the lift off distance here and the takeoff run from here to here, and this is the engine failure at V1. And if in this point the aircraft have the engine failure and the pilot decided to stop the aircraft, so the aircraft will be going here to the stopway. So from here to here is a decelerate stop distance, because from here the pilot decided to stop the aircraft, and we call it with accelerate stop distance, or ASD. From here to here is DSD, from here to here is accelerate stop distance. And if the pilot decided to continue the flight or the takeoff, so the pilot will go here, the aircraft will go here, and this is in the height of 35 feet from the ground, and this is for the takeoff distance from here to here. So the takeoff distance is the runway plus the clearway, and this is the equation to find the TOD, CL, TOR, and FS when the engine failure takeoff cases, and if the engine failure about the takeoff cases is using this equals. So the last is for normal landing cases. So the landing distance required for an aircraft must be sufficient to permit the aircraft to come to a full stop. So this is the landing distance from here to here, and there is also the stop distance from here to here, and the stop distance must be 60% of landing distance, and we should have to assume that the pilot makes an approach at the proper speed and crosses the threshold of the runway at a height of 50 feet. Here, from here to here is the distance is 50 feet, and the landing distance must be a full strength pavement. And this is actually for the turbine aircraft, and the piston aircraft is the same. So this is the vertical alignment. So this is the runway, and from here to here is the landing distance, and from here to here is a stop distance. This is 60% of the landing distance. The stop distance is the distance that accommodates the aircraft to stop, so it will stop here, the aircraft, and assuming that the pilot will take a landing from the threshold is 50 feet from the ground. And this is the equations for the landing cases. So after we know the three cases, we should have to determine the required field length and the various components of length, which are made up of full strength pavement, stopway, and clearway. The above equations must each be solved for the critical design aircraft at the airport. This will result in finding each of the following values. So we should have to find these values from the FL is the maximum number of TOD1 or TOD2 or DAS or LG, and as for the FS, we should have to find the maximum number from TOR1, TOR2 and LG, and as for the stopway or SW is DAS minus maximum number of TOR1 or TOR2 or LG, where SW minimum is 0, and the last is the CL or the clearway is the minimum number from FL minus DAS or CL1 maximum or CL2 maximum, where CL minimum is 0 and CL maximum is 1000 feet. So this is the values that we should have to find to determine the length of the runway. And if the operations are to take place on the runway in both directions, as is the usual case, the field length components must exist in each direction. Now is for the example. Please determine the runway length requirements according to the specifications of FAR 25 and FAR 121 for a turbine-powered aircraft with the following performance characteristics. So because this is for a turbine-powered aircraft, there is three cases: normal takeoff, engine failure, and normal landing. So this is the data given. For normal takeoff, the lift-off distance is 7,000 feet and the distance to height of 35 feet is 8,000 feet. And for engine failure data is the lift-off distance is 8,200 feet and distance to height of 35 feet is 9,100 feet. And for engine failure aborted takeoff, the accelerated stop distance is 9,500 feet, and for normal landing, the stop distance is 5,000 feet. So this is the answer. For a normal takeoff, let's calculate the TOD1. The TOD1 is 1.15 multiplied by D35.1, or the D35.1 is here 8,000 feet, so we multiplied it, so we know it 9,200 feet, and then we calculate the CL1 maximum is 0.5 multiplied by TOD1 minus 1.15 multiplied by LOD1. So let's calculate it. So the TOD1 is here, 9,200 feet, and for the LOD is this lift off distance 7,000 feet. So here, and it is equals by 575 feet. So now we will calculate the TOR1. The TOR1 is TOD1 minus CL1 maximum. So this is 9,200 minus 575. It equals by 8,625 feet. So this is the TOR1 for a normal takeoff. So now we will calculate for an engine failure takeoff. The TOD2 is T35-2, or this, the distance to height of 35 feet or 9,100 feet. Now we calculate the CL2 maximum is 0.5 multiplied by TOD2 minus LOD2. The TOD2 is here, from here, and the LOD2 is from lift off distance is 8,200 feet. So we calculate it is equal by 550 feet. Now we calculate the TOR2 is TOD2 minus CL2 maximum is from here, 9,100 minus from here 450. So it's equals by 8,650 feet. This is TOR2 for an engine failure takeoff. So let's calculate for an engine failure aborted takeoff. So the DAS is 9,500 feet from here, the accelerated stop distance or DAS. So now calculate for a normal landing. The LG is SD divided by 0.6. So the SD is stop distance is 8,000 feet and divided by 0.6, and this is equals by 8,333 feet. So this is LD for normal landing. So using the above quantities, so the actual runway components requirements become, so for FL is maximum from the TOD1 or TOD2 or DAS or LD. So we look for the maximum number. So the TOD1 is 9,200 feet. As for TOD2 is 9,100, and for DAS is 9,500, and for the LG is 8,333. So we look for the maximum one is this one, or DAS is 9,500 feet. So this is for the FL. Now we calculate the FS. So it's the maximum number from TOR1 or TOR2 or LG. So the TOR1 is 8,625. As for TOR2 is 8,650, and for LD is 8,333. So we look for the maximum number. So it is here, the TOR2 or 8,650 feet. This is for the FS. The FS is full strength pavement. So let's calculate the SW. So SW is DAS minus maximum number from TOR1 or TOR2 or LG. So the DAS is here and minus maximum from the TOR1, TOR2 and LG. So we get 850 feet for S-way or SW or the stopway. And as for the clearway, is the minimum number from FL min DAS or CL1 maximum or CL2 maximum. So we'll look for the minimum number from here and we get 0 feet for the clearway. Now we will draw it. So this is the runway, this is the stopway. We don't have the clearway because it's 0 feet. So this is for the FS or the full strength pavement from here, and this is for the stopway or SW. This is from here, and the FL is here from the FS plus the SW. We get here at 9,500 feet. So as for the FS or the runway is full strength pavement, and for the stopway is partial strength pavement. Now is the exercise. Please determine the runway length requirements according to the specifications of FAR 25 and FAR 121 for a turbine-powered aircraft with the following performance characteristics. So this is the data, and please calculate it. Okay, that's all for this meeting. After this, I hope you will understand what is the effect of aircraft performance on runway length. Okay, thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.